So hi everybody. So this paper I chose as the baseline for this paper show, attend, and tell neural image caption generation with visual attention. So from ICML 2015. So first let's see a simple example. So given this image, then we try to generate an image caption. So that's a person sitting at the table and there's a plate of food. So this the dark and bright area shows the attention. When we generate each word, where the attention goes.
That's enough.
Yeah. Yeah. So this is a very traditional encoder and decoder framework. So we also mentioned this paper before. So this one is very straightforward and simple. So first, we put an image and encode it with the CNN, then decode it with the LSTM. So it's like translating the image into a sequence of words. So let's go into the model detail. So we first define the task. So the task is put a raw image and generate a caption Y. So the Y is the sequence of one of K encoded word. So the C is the length of the sentence. And then the encoder, we use a convolutional feature by CNN. So here we take the A is the annotation vector. So here the A, we use the feature extractor to get L vectors. So here there is an L vector. Each of the vector AI corresponding to a specific part of the image. So this one will be helpful in the attention part. So we don't take the feature from the fully connected layer because we want to still obtain some 2D location information of the raw image. So we take the feature from the lower convolutional layer. Then there is the decoder. It's LSTM. So this is the formula. We have the input, gate, the forgets, and the output. So YT here is the state. We have the sentence we generated so far. So here there is the ZT. So here actually the ZT is the true input. So the ZT here is the context vector. So this one capturing the visual information associated with the particular input location. So because the intuition is when we generate a specific word, there is something important in the area in the picture we need to focus on. For example, when we predict there is a man sitting or something, so the man specific, we need to put attention to the man in this area. Then there's the context vector computed by this formula. So here the AI is the specific portion of the image feature. So in the particular space. So remember, so we divide the image feature into different L vector. So each vector corresponding to a specific area. Then the alpha I, so here corresponding to some, we can say the importance or the probability that this area we should put right attention to when we predict the next word. So there are two ways to generate the attention. So one is called the hard attention. So here so Y is a sentence we generate so far. So A is given the area of the image, so the feature area, the specific one. So here we use this as the log probability of the AS as the loss function. So in this way, we train the attention. So here we can get the phi. The function give us a sampled alpha I. So alpha I is at every point in time based on the multilinear distribution. So whether, so it's if you train by this hard attention, so every image, every part is whether true or not. So like we can see the example later. So then there's corresponding to the hard, there's the soft attention. So given this, then the expectation, so we take the phi as the expectation of the context vector. So here's like the alpha I is not choose or not, it's like a expectation, so it's like a weighted annotation of the whole image. Then we can see an example here. So this one corresponding to the hard attention. So when we talk about bird, so this bright area shows where the attention goes. And if you take a soft one, then it's like you can take the weighted area of the raw image. So let's go back again. So it's very simple and straightforward. So first get the CNN, put the image into CNN. We have the annotation vector of the image, so denoted as AI. Then we put the attention, generate the attention, so each word corresponding to which part of the AI. Then we put all this thing into the STM. Then we can get the caption. So this is the experiment result. So the author tried two different attention ways, so like the soft and the hard. And basically all the attention, if we add the attention into the framework, so the result improves a lot. So like for the BLEU criteria, like the hard attention is better than the soft one. But if you take the different criteria, like the soft attention gets better. Okay, so this is the review question. So okay, so first thing is like when talking about the contribution of his paper, is like a reward defined by the visual-semantic embedding. So we take a look at this is the baseline, and this is like the baseline with the embedded reward, right? So somehow, so actually the result sometimes improves, but sometimes so like yeah, this one sometimes it decreases. So I'm thinking why is that whether this reward defined by the author is really good. So like according to Charles, like maybe you should do some pre-processing for the image or some other thing. So or maybe use some other reward like people used before, because this one is presented by the author. So this is the first one, the question about the reward. And the second one is about error analysis. So when we use the attention part, so we see for this, so for example, this picture, like a man wearing a hat. So here the skateboard is the mistake, right? Then we go back to see the attention. Oh, we see, so must be something wrong with the attention. So like attention in the right place, but get the wrong items. So maybe he recognized the item wrong. So this attention help us to understand the mistake in a more visual way. So like we can get. But if we take of this one, so the reinforcement one, so we get the error. But how to analyze the error? So is there a good way to, like let's for example, let's go back to the value network or the policy network. Is there anything there can help us understand why we made this kind of mistake? So the last one is about the network architecture, because the value network, this part, and the policy network and the value network. So like you need to do some pre-training, then like join training together. So this part contains like CNN, RNN, yeah. So is there something they can share together, like they can learn together? So because this like a complicated network, so you need to train 3 of them. There is also embedding, the reward, the embedding one. So yeah, that's all my question.
Yeah. Okay, okay, I'll get somebody to come down and get it. Yeah. Okay. Go to the right. Where is it? Subway. Do that. Okay. food deliveries.
That's the answer. I have food.
Let me see my friend.
So we don't have any questions, right? Jingyao.
Oh,
Yeah, any questions for
yeah.
Jingyao first?
We don't, right?
Is the paper that we presented will compare to this paper?
Yeah, actually there's one result like they use the same Microsoft Cocoa data and they calculate this BLEU one.
Hello.
Somehow
Hello, yeah?
this one performs better than this one, but that's the only one. So according to the author, like maybe because they use different pre-processing of the word.
Which part?
So the author also don't know why.
Where you are?
Yeah, I have one.
Oh, taxi stand. Okay.
Actually, as you want, you show that
Okay, ask
somehow
me.
in the hard attention and the soft attention,
Yeah.
there are some the case the pictures.
Yeah,
Yes,
yeah,
here is somehow like the top one is the soft attention. Right?
yeah.
It's look better than the hard attention. But
Yeah, but actually, yeah, this one like corresponding to different part, but they all both generate the same sentence.
Yes.
Bird flying over.
yes,
So,
the point is after you move to change to the table, you showing the table to
Yeah,
the
yeah, yeah.
table. Somehow the hard attention is better a bit than
Yeah.
the soft attention. Any explanation?
Yeah, right? It's
Yeah.
common sense, right?
Yeah.
Hard
Can somebody go to taxi stand?
assistant.
Library.
No, downstairs.
Oh, it's like who's collecting?
Because I think there's too many.
Oh,
You say it's quite big.
Only to change it.
they,
Yeah.
oh, Huang is calling.
Hello. Hello.
Yeah,
There's
so
one more at the taxi stand.
I think like when you generate a specific
Okay,
word,
okay,
so maybe the only one part is important. Like you don't need to care about the other part. So like for example the A bird, the A part, so actually it's that difficult. Like you don't need to take the whole look of the picture. And but if they use different criteria to check whether the result is better or not, they get different ones. So like somehow if you compare with the like METOR, the soft one is better.
But only the last one, right?
Yeah, that's like a different one to check whether this one is better or not.
Yes. So somehow you see the two different pictures on the two documents.
So hard actually if you
Yeah. But in the picture it's
Yeah, it's
yeah.
right.
So, okay, I have a question to Tony. You said the first attention looks better, right?
It look better.
Like, how this attention is supposed to generate the A, the first word? How the attention is at all related to A?
But he said about the explainable properties, right? Well, explainable properties
Okay.
of
Yeah.
this
It's-
model. So he claimed with. I mean, he
Yeah,
asked the
but-
question for win, right?
You want to generate A, it's and the attention goes to your wings, right? And how is it supposed to? How is it related? How is it
Or maybe
related?
there's only one object there. One object there, so it's A. I don't know, but actually,
But I think the attention is not always work like directly to the thing we need to pay attention to. So, but in general case, like for example, the holding a skateboard or something, so that's where the attention goes. So that one helps.
If it doesn't work always the way,
No, but how?
why do we even need to print these things? Why do we even need to show this?
You can see the difference between hard and soft. I mean, they don't have to show the bird, but they can see the diffusion.
The diffusion. Okay. And but this attention pays to the touches of the images. So the diffusion of the difference.
Maybe Actually use a complicated image, so not only a bird, a man sitting a horse.
So it confuse you.
Yeah.
But actually, somehow, let's say for the short testing is better, right? Let's say at least the bird, they just show a highlight on the bird, right?
But we don't
Flying.
know if it's better, right? We don't know if it's better. So we don't know what the attention is paid to the convolution layer, right? It's not to the image, actually.
I think probably
Or is it to image?
To the lower convolution layer.
Lower convolution.
Yeah.
We don't know what the convolution layers.
I think for this image, it's not a good example. I think
Yeah.
probably they focus just on the part where there is a lot of variability.
Yes.
So the water part, you always get the same values. Then you can't really decide anything.
Yeah, but no, then how is it related to the words we generate?
But actually, for the model, when the model shows you
publish in
that,
CDPR without an image, you needed to show that there are some photos that you're working with.
but actually, they use this attention, these areas to learn the context, better context.
Yeah,
right,
but
later, right?
We don't know what the lower convolutional layers learning. We don't know what the attention shows us. So why do we bother to try to interpret it?
like, like this is the soft one, right? So you see this
Yeah,
is
it goes to LSTM, and LSTM, we don't know what's happening with LSTM.
but
But
this like
it works. So okay, we run out of time.
He hasn't responded yet.
Oh yeah,
Yeah,
or
yes.
I have more questions.
Okay, first question. Remote defined by visual semantic embedding. Yeah. So as they said, the semantic embedding doesn't really help. The most of the contribution comes from the value network, and of course there's some. I think there will be some discrepancy in the embeddings because I don't think the embedding is perfect. There can be many things done, like just now Chong said it could be have different parts of the image in the embedding as well, because the image can be made out of multiple like noisy, right? So I guess this is the part where the embedding fails, because there can be more than one object or items inside the image, and the embedding can't fully represent the whole image. Yeah, that's what I think. But so, what do you want to know how to improve it or?
yeah, I just have a question about whether this reward truly can present the similarity between the
Yeah.
words. So like, is it really helpful
Sure, of
or
course.
use like a different?
I think right now, this is one of the embedding which can help to find the similarity between these two. I mean, you can go further to use to train some other network, but their authors are not looking for something that is very good, but something that can help you represent the different states of the thing to a certain reward at the end. So I guess this is one of the networks that help. And yeah, as they say, they will try other embeddings to improve the score. So at the end, I said that, and the authors actually said that as well. Yeah. So I think the embedding can be changed. So that's not a problem. Yeah.
Can I ask a question
Yeah.
there, or I can't?
Go ahead.
Why blue is a good metric for this task? And what is native or rouge and cider?
Okay. So interesting question. They are just actually most of them are the same. It's just different metrics. So how they match the distance between the image and the different strings. Yeah. So
then why blue? Blue does make sense for machine translation. Right?
Okay,
That
yeah.
I know that is experimented and justified. Why does it make sense for image captioning? Because I would think when we translate the things, right, there is less variability how we can translate the things than in generating the caption of the image.
I mean, this is the current baselines, and
But there's only one ground truth, right? Is that right?
what do you mean by one ground
For
truth?
a given image,
Yeah, there's
they only
five.
give you
There's
there are
five or more.
There are 5 or more captions.
Yes, correct. So yeah, so different. I mean, different distance. But this is the standardized baseline for all this image captioning. And I guess nobody has came up to question why they use this baseline.
So what do they do with the 5? Do they take the best one?
I think they use all 5 because the image captioning tool.
So how do you use all 5?
This is a good question. But because the Microsoft Cocoa tools does the analysis and comes up with this.
I mean, do they average it? Do they take the best one?
I'm not sure.
The
So,
average, the metrics, right?
yeah, the metrics, like
For
the
a given
different
image.
captions.
For a given image.
Or given.
Then that's wrong, right? If you say that they are variable captions, then you should approximate the best one.
Like me.
Because you can't possibly generate 5 of them if you don't allow them to generate 5.
Isn't it like the generated caption is the summary of all files, approaches, and captions?
But the generated caption only gets an image. It doesn't get anything else, right?
Yeah, but the caption, I mean, the caption might be the same as well because it's generated by 5 different people for that one image.
So, but it can also be different.
Yeah, it can also be different.
Oh.
Yeah. So, I'm not sure whether they average it or they take the best.
I
This
mean,
one-
you may see the bird, I may see the water, right?
Yeah, I understand. But if there's both, it's the best. The bird flying over the water.
They don't talk much about the pre-processing of the Cocoa data.
Yeah.
So they just say they use the same pre-processing.
But what's wrong with the blue itself? It's just looking at the bird.
You say there's
Yeah.
And looking at the bigrams, right?
Right.
So I would expect the machine translation bigrams make sense in the generating the caption. It doesn't make sense.
Well, if you believe that there is a ground truth sentence, then it makes sense. If there is an ideal sentence.
But
Just like a
really,
translation, you can have multiple translations. to the
Yes, but
same
they're
one.
all less variable. That's why we compute blue 4, and it makes sense because we match forwards. We are good at the same time, right? Here, what I see is that blue 1 is actually what do we improve? We improve from SL to SL event. We improve blue 1. Which doesn't make I don't know. Does it make sense to improve the blue one? Or doesn't it make sense?
Is it even improving?
yeah.
A little bit.
Yeah.
I mean, don't even know. Is it, but
I think there is a lot more variability when I look at the picture and someone asks me to describe.
so it depends on the picture.
it.
How complicated
I
it is.
agree,
Yeah.
but I'm comparing it to the machine translation task where the blue it was developed for machine translation task, right? Header was
Understand.
developed for sentence summarization, rouge was developed for sentence summarization, right? For text summarization, I don't know what the cider is. And I say that the blue is probably not a good metric. I'm not sure about the meteor. It probably make
So
little
you say
more sense.
you say there should be one developed just for image captioning.
I think they should explore this question. Does it has the same properties as machine translation?
Maybe not, yeah. Because there's different ways of saying the same thing about the image.
Because blue was a revolution in machine translation. Is it a revolution in image captioning?
It's
The
this
question
are
is whether we
yeah.
can have a better metrics, right?
I
Whether
mean,
we can
it's-
find a better
Yeah,
metrics.
I mean, the group that justified, they asked some people to translate. They found that there is a correlation with the good translation of blue 4.
Okay. So maybe they have to do a study on blue with image captioning.
I mean, this is a CVPR paper, right? They will just say, let's take whatever the other people say is good.
And how do I read the results? I compute 6 metrics right here. How do I read the results? One's a good, one's a worse.
But we compare with other baselines. So if all these baselines are good compared to the other ones,
This doesn't tell anything.
it's still good. It's good, right?
It's good on something, right? But we don't know what it is good on.
I mean, if you get a perfect score, essentially you would have...
You generate the same captions.
Right, you
Which
generate
might
the
not
same
be true,
captions.
right? Because there might be a better caption.
But that's the same actually. In the translation, there might be better translation. You just deal with the data that you have.
Yeah, what I'm saying, there is a variability of translation. I'm saying that in translation, the variability is less than in generating a caption for image.
No, but that has, you can see it empirically, right? So it might well be that the 5 captions are the same. So for the kind of images that they put in, I don't know, what is that thing?
So then I would like to see this.
You can see the images just now, like I showed
Like a bird, like a bird on water.
Yeah, like a dog on yeah, and a cat and stuff like that.
So I can say that the dog on the grass, or grass with the dog.
You
in
can't
translation, I have-
you can't say the grass.
Whatever. In translation, I have only one way to translate it. Very simple sentence.
I can't argue with that. Shall we move on? Or do you have a question?
Yeah, I have a question. Like, are these two papers solving the same problem?
Sort of, yeah, because they are all captioning images.
Not the bigger task, but I think the paper you presented, that the reinforcement learning framework is to solve an issue of
Yeah, correct.
previous
The
approach
correct.
for
So it's the
captions
yeah, correct. It's the greedy and the look ahead, the beam search. So do you want to replace the greedy and the beam search with this value network?
I think that probably related to your question because they use greedy and beam search to generate the possible sequence. So they don't actually look through all the possible sequence. They will cover all the solution space. So that's why they need value like that reinforcement framework to improve that issue. If you can work on the full solution space, then probably supervisor case can be better function. Yep, that's you said right. The dictionary is
Yeah, it's large. It's very large.
The access value is
Because it's not only the dictionary, but also the subsequent words after that.
Mm.
The kind of word.
The
yeah.
state as well.
Yeah, correct. It's huge. So, I think Maxim already talked about this just now, right? Why look at okay.
The event and the head of the. Okay, so it's not an example.
Okay, so for this, you actually kind of can, because you can break it down to both the value and policy. So the policy itself can come from this. This can be one of the policy for this reinforcement learning. So if you ultimately decide to use this policy, then you can possibly look at the attention. Yeah, but of course for the value network, it's slightly different. It's harder to decode. Yeah, but yeah, it depends on the embeddings. So there's that. Maybe it's slightly harder to analyze, but if they want to analyze the policy network, it's still possible. Yeah, and there's a lot of analysis to do with hyperparameter tuning as well, because there is now a hyperparameter between the trade-off of policy and value network. So yeah, that as well. So they need to analyze all this. Yeah, so I can't really say much about that. Okay, network architecture. What's this?
So like they use
a lot of, is there a shared components, right? You said?
Yeah. Can I share part of the?
Well, if you want, you can, but then it might not be as good of a score as if they are separate. Because let's say you use something that, like, you train CNN with autoencoder as an autoencoder to encode the image to the same output, then you can use the same CNN. But then it's not specialized for your task, which means that it might generate a lower score. Yeah, if you share the CNN. So if you use a CNN as an autoencoder, then you probably can use a shared system. Yeah. But then the CNN is now not specialized. Yeah. You can, but yeah, I think they optimize for score. Yeah. So, any other things you want to know? Yes.
So this one train independently first, like pre-train first.
Yes, pre-train first.
All of the value network, the policy network, and the reward of
Oh.
the embedding.
Oh, embedding is only separate. There's no joint training for the embedding.
Okay.
Yeah. And the embedding one you can use the same CNN if you want, using autoencoder, and then you create a generalized CNN, possible, but the score might not. Yeah. That's good. Good.
So Jingyao, what advantages that you claiming for the paper that you presented?
Simple, it's straightforward, and the result is good. But like there's only one thing, this one more like 3 of them.
Yeah, 3. Yeah. Any questions from the floor? Okay. Done? Okay. Yeah.
Alright, let's thank both of them.